When the contents of Anthropic's Claude code repository hit the internet, the initial reaction pointed to a sophisticated breach of the core model. No zero-day exploits were involved. The containment layers held. The base model weights remained entirely secure, and no user data was exposed to the public. This diagram shows what actually leaked: the orchestration layer. We got a direct look at Anthropic's system prompts, their specific tool schemas, and the guardrail instructions that steer the model's behavior. Modern enterprise AI products operate by wrapping a probabilistic core inside a rigid, deterministic orchestration architecture. The model generates possibilities. The architecture dictates the reality. The hidden weights give a model its raw intelligence, but this orchestration layer contains the routing logic and safety controls that make the product viable. That structure is the actual intellectual property. The exposure happened through a mundane DevSecOps failure. Someone misconfigured repository visibility and pushed internal scaffolding tools to the public web. Obsessing over locking down model weights creates a false sense of security if the surrounding systems are left exposed. The real attack surface is the integration layer. We need to look closely at the prompt scaffolding. In a production environment, you do not interact with a model through a simple, open-ended chat window. The leaked files revealed highly structured role separation. Anthropic relies on version templates to dictate exactly how the model should interpret and process incoming data before it ever sees a user's query. They use injection-resistant formatting. By wrapping inputs in strict XML or JSON tags, the system forces the model to treat user text as isolated data payloads rather than executable instructions. Tone enforcement and behavioral constraints are hard-coded into these same templates. The prompt defines explicit boundaries on what the model can acknowledge and how it must structure its output. Before generating a final answer, the model is routed through reasoning control mechanisms. It is instructed to output its step-by-step logic into hidden internal blocks for evaluation. This creates a physical architectural boundary between the model's internal reasoning phase and its outward execution phase. The system can audit the logic before triggering a visible action. Enterprise prompt engineering is rigorous software architecture. It is built entirely to cage the inherent unpredictability of a large language model. Moving outward from the prompt templates, we hit the external execution layer. This is where the model is granted permission to interact with outside APIs and execute tools. This flow illustrates schema-constrained tool calls. Every request must conform to a strict, predefined structure to pass the filter. Explicit JSON formatting is enforced at this boundary. The execution layer requires machine-readable predictability, rejecting any output that deviates from the schema. Without an enforced boundary, a malicious input can trick the model into writing its own arbitrary commands, executing code directly on the host server. A weak schema also invites privilege escalation. A model given access to a benign search tool might pivot and access an internal database if the execution layer lacks strict logical partitioning. Then there is the risk of cross-tool data bleed. If isolated functions share an open memory space, sensitive information retrieved by one tool can contaminate the inputs of another. To prevent this contamination, tool responses undergo controlled injection. The raw data returned by an API is sanitized and explicitly formatted before it is fed back into the model's reasoning layer. Without hard physical and logical schema constraints around execution, an AI agent functions as a high-speed liability engine. The structure exposed in the Claude leak perfectly illustrates the cybersecurity principle of defense in depth. Anthropic does not rely on a single filter to catch bad behavior. This structure models multiple layers of defense. First, prompt constraints restrict initial behavior. Second, the reasoning format forces auditable logic. Surviving anomalies hit three final layers: tool-level validation, output post-processing to scrub formatting, and runtime monitoring hooks tracking execution. AI safety is a structural architectural property. It requires a heavy, multi-layered gauntlet. You cannot achieve this by toggling a single moderation API. Yet a simple misconfiguration bypassed this entire gauntlet. The leak did not defeat the defenses. It walked completely around them. Accidental public pushes of internal tooling and poor repository visibility settings expose the exact logic that powers the defense system. When engineers fail to strictly separate their development sandboxes from production environments, experimental scaffolding ends up mixed with live production configs. The industry operates with a massive blind spot. Engineering teams meticulously encrypt database passwords and API keys while leaving their system prompts and tool schemas sitting in casually secured repositories. The greatest existential threat to modern AI products is mundane, classic software engineering negligence. We should treat the Claude code exposure as a technical blueprint for defensive agent design. It provides a clear set of rules for securing the integration layer. Rule 1. Treat system prompts as production code. Secure them with least privilege repository access, ensuring only necessary personnel can view or modify the architecture. Rule 2. Enforce strict schema validation at all tool boundaries. The execution layer must automatically reject any malformed request from the model before it reaches an external system. This architecture maps out Rule 3. Physically and logically separate the reasoning environment from the execution environment. Keep the model's logic isolated from its ability to act. Rule 4. Design your system architecture with the baseline assumption that your internal prompts will eventually be exfiltrated. Secrets leak. Your logic will be exposed. Rule 5. Rely on structural resilience. Depend on your output shaping and rigid validation layers, rather than relying solely on the secrecy of your prompts. If your system's safety collapses entirely because a user views your underlying system prompt, your core security model is broken. Anthropic took a temporary reputational hit, and the public rightly scrutinized their internal orchestration hygiene. The resulting industry shift moves the focus from protecting hidden model weights to auditing the AI supply chain and securing the orchestration layer. Enterprise builders are accelerating their awareness of prompt injection risks and mapping out the exact mechanics of tool call boundary abuse. Real-world AI systems are deeply engineered glue systems. They rely on rigid routing logic, structured formatting, and safety layering. Evaluate your own production architecture. Look closely at how you are isolating your tool execution environments today, and ask yourself what happens when your prompts inevitably leak.